Hello, my name is Johnson Nilisheri and welcome to my YouTube channel Nilisheri Designs. Today we'll look into the design of the spigot socket type of cotter joint. This is the picture of Don Bosco. This is the picture of Miss Alfonsa Lona Collegieri. It is required to design a spigot socket type of cotter joint to transmit an axial load of 42 kN. Cotter joint is used to connect piston rod in crosshead in steam engine. Select appropriate material for its components and draw a sketch showing major dimension on it. Here we can observe the steam engine, and at one side we have the crosshead and the other side we have the steam cylinder. In between we have the cotter joint. You can see a projected part here which is the cotter in this picture. The cotter joint consists of three parts. One is the socket, the other is cotter pin, and the other is spigot. So these are the three important parts in the cotter joint. Let us look into the cotter pin. Cotter pin is a temporary fastener which is used to hold two parts together, where parts are subjected to external axial forces only. Cotter pin is wedge-shaped piece, that is, the taper is provided only at one end. The other end is straight and is without taper. For other design videos, refer to the link provided in the description of this video. You can do a YouTube search of this particular videos with the name Johnson Verghese Design. Also, you can find question paper in the playlist. Let us look into the spigot end. The spigot end consists of three parts. This is the spigot cylinder which has a slot in this. This particular part is called as the collar end of the spigot, and this particular part is called as the rod end of the spigot. Let us look into the socket part of the cotter joint. This particular end is called as the rod end of the socket. This particular part is called as the socket cylinder which has a slot, and this particular part is called as the collar end of the socket. One important observation here is that majority of the slot lies in the cylinder part of the socket, and partial slot is also present at the collar end of the socket. So both of them have slots. Let us look into the tree diagram of the cotter joint. This tree diagram consists of different parts and the stresses acting on those different parts. Now this part is of the spigot, and this spigot rod is subjected to tensile stress. Spigot cylinder is subjected to crushing stress, tensile stress and shear stress. And the spigot collar is subjected to crushing stress and circumferential stress. Now the socket consists of different stresses. The socket cylinder is subjected to tensile stress, socket collar is subjected to crushing and shear stress, and socket rod is subjected to circumferential stress. The last part is the cotter pin, and the cotter pin consists of shear stress and bending stress and some accessories. So this is the tree diagram which will help us to remember the design. Let us look into the 2D diagram of the cotter joint. This part is the front view, whereas this part is called as the side view. In this figure, you can observe that capital P is the applied external axial tensile force that is applied on this particular cotter joint. Here, small d is the diameter of the rod. D1 is the diameter of the spigot cylinder. D2, here is the outside diameter of the socket cylinder. D3, which is placed here, is the diameter of the socket collar, and D4, which is here, is the diameter of the spigot collar. Here one can observe small b. Small b is the width of the cotter, whereas T is the thickness of the cotter. The T1 dimension here is the thickness of the spigot collar. You can observe here A, small a. Distance from the end of the slot to the end of the spigot is called as small a. C1 is the thickness of the socket collar, and C here is the partial thickness of the socket collar. Here you have L1. L1 is the length of the rod within the socket. So these are the parameters in the cotter joint. Here we have listed out the different parameters that are used in the cotter joint, and these are few other parameters which are listed in the cotter joint. Let us look into the free body diagram of the knuckle joint. The knuckle joint is designed on the base of free body diagram. The free body diagram is constructed using the principle that actions and reactions are equal and opposite. The sum of all forces acting on individual parts must be equal to zero. So these are some principles on which the free diagram are based on. Let us look into the figure where we have capital P acting on the left hand side and right hand side, and these are the applied forces. Because of these applied forces, induced forces will be developed within the components. Let us look into the socket. In the socket we can see a force P is acting on the left hand side, whereas P by 2 force and P by 2 force is acting on the right hand side. So the addition of these two forces P by 2 and P by 2 will lead to P, and the P at the left hand side and right hand side will cancel out each other. This particular component is in equilibrium condition, and it displaces the force acting on the component. Similarly, if you look into the cotter joint, we can see a force P here on the left hand side, and you can see P by 2 and P by 2 forces on the right hand side. So we can see that their directions are opposite and the magnitudes are same, hence they cancel out each other, and this is the forces that act on the cotter joint. Here on the spigot we can see the force that is acting in one direction, and the other force on the spigot is acting in the opposite direction. Hence they cancel out each other. Hence in this way we can understand the forces that is acting on the different components of the cotter joint. Let us assume that all the parts of the cotter joint are made of the same material. Take the material as plain carbon steel and the grade is C40. The tensile yield strength for C40 can be taken as 33 kgf per mm square, which can be converted and simplified as SYT is equal to 330 Newton per mm square. The factor of safety depends upon direct action load and stress concentration factor. The direct action load is taken as 2 and the stress concentration factor is taken as 1. Hence, the final factor of safety is taken as 3. So, in all further calculations, the factor of safety will be taken as 3. The design tensile strength is designated as permissible tensile stress for socket, spigot and cotter. For all the three parts, it will have the same design tensile stress as all the three parts have the same material. So we will take the same thing for crushing stress. So we have the design crushing stress and the design shear stress. All three of them will have the same material, and since the design crushing stress is also taken the same for the three parts. Let us calculate the permissible stresses here. The permissible design stress is equal to the permissible bending stress. So this is an assumption clearly made here. When we substitute the value of SYT and FOS, the value comes around 110 Newton per mm square. The permissible shear stress is equal to permissible design stress upon 2. So this value comes around 55 Newton per mm square. Similarly, the permissible crushing stress is equal to design stress multiplied by 1.3. The value comes around 143 Newton per mm square. So these are the values for the material, and since we have three different parts and all the parts have the same material, we will be using the same permissible values in the equation. The assumptions in the cotter joint are as follows. The rods are subjected to axial tensile force. The material is homogeneous, isentropic, and obeys the Hooke's law. The effects of stress concentration due to slot and steps are neglected. Since due to hammering of cotter into the slot, which we call it as a wedging action, the stress due to initial tightening of the cotter in this particular case is neglected. Let us start the calculation with the design of the rod. Here what we see is the socket, and the socket at this particular section is the rod part of the socket. And if the due to the tensile stress, if this particular rod breaks along the section A, we get a circular cross section in this manner, which has a diameter of D. So we have our equation, whereas induced sigma T is equal to P upon area, and this particular ratio should be less than the permissible sigma T. We know the value of permissible sigma T. We'll substitute the value of P and we will find out the value of D here. So D comes around 22.048, which can be approximated as 23 mm. So using the design strength equation, we have found out the diameter of the rod. Let us calculate the spigot dimensions. So here we can see the spigot, and the spigot is connected with the cotter pin, and because of this the crushing stress is induced at one edge of the spigot. As you can see here, the red color area is the where the stress is induced due to the cotter pin. So this particular area we can see here, where D1 is the cylinder diameter of the spigot and T1 is the thickness of that slot. So this equation can be developed where the induced crushing stress is equal to P upon projected area. The projected area is D1 into T, which should be less than the permissible crushing stress. So now we will try to put the values in the particular equation. We'll substitute them. We know the value of P, which is 42 into 10 raised to 3, and we know the values of permissible crushing stress, that is 143 Newton per mm square. So when we substitute, we will get the value 293.70. Now here D1 is also unknown and T is also unknown. So we need one more equation to find out the individual values of D1 and T. In this case, due to the tensile stress between the spigot and the cotter, this particular part fails. We can develop the equation for the tensile stress as P upon area. In this case, let us take first the whole area. The area is pi by 4 d1 square, and this particular area where the cotter is to be placed need to be subtracted. So the length of this area is d1 and this thickness is t. So we will subtract d1 minus t. In this manner, we will develop the area for this case. In this slide, we can observe the section whose area we have just formulated. We'll go to the next slide. In this particular slide, we will substitute the values. So let us see here, we know the value of t, and in the previous equation, we had found out what is d1 into t. So we'll substitute the value of d1 into t here, 293.70. We know the permissible tensile stress value, and after simplification, we can get what is d1. So after putting it into the calculator, getting the values, D1 comes around 29.32 mm, which is approximately 30 mm. Now again resubstituting in the formula, we know this particular equation earlier. We will substitute the value of D1 and we will try to find out the value of T. So the T value can be approximated as 10 mm. Hence we have found out D1 and T, both the parameters. In this particular case, the double shear stress induced in the spigot due to cotter pin. Now we can see in the 3D view where the spigot is subjected to cotter pin, and because of the forces, this particular area gets abraded off. So here we can see the area where the diameter is given as D1. Here the A is the sheared parameter or the sheared length. So the area becomes D1 into A. Now we can also observe in this 3D view, there are two areas, one area at the front side and the other area at the back side. So there are two areas that gets abraded off or sheared off, hence the two will come in the formula. So hence the induced tau is equal to P upon A, where the area is 2 into A into D1, and the ratio should be less than the permissible shear stress. This is the 2D picture of the double shear. Here we can see the cross-sectional area of the particular component. Now let us substitute the values. In this whole equation, we are not aware of the A parameter which needs to be calculated. After substituting the values and knowing the permissible shear stress, we can find out A as 12.72, which can be approximated as 13 mm. Here we look into the crushing stress induced in the spigot collar due to socket collar. In this particular case, the spigot is subjected due to the socket collar. Here, the ring-like section will be subjected to crushing stress. Now, this particular crushing stress area is denoted in this figure. The blue color denoted in the figure is the area where the crushing stress comes into picture. To find out the area, we have to calculate the outer area and subtract the inner area from it. So the outer area, we need to know the diameter. The diameter is D4 there. And the inner area, the diameter is D1. To calculate the area, we will consider pi by 4 D4 raised to square minus pi by 4 D1 raised to square. So in this manner, we will find out the area in this case. Now we will substitute the values. In this equation, we know the value of P and we know the value of D1, but we need to calculate the value of D4. Putting all the known values, D4 can be calculated, which can be approximated as 36 mm. Here, the circumferential shear stress induced in the spigot collar due to socket collar. So one can observe in the figure that due to socket collar, the spigot collar gets sheared off. So this ring-like section gets sheared off, and the red color area here is the resisting area. So we need to calculate this resisting area. The resisting area is denoted here, where D is the diameter of the resisting area and D1 is the thickness of that particular area. So we can write it in the form of P upon A, where A is pi into D1 into T1 and the ratio should be less than the permissible shear stress value. Here we will try to substitute the known values. In this equation we know what is P, we know what is D1 and we know what is permissible shear. So after substituting the known values we can find out T1. Now T1 is 8.10, which can be approximated as 9 mm. The stresses acting on the socket are the tensile stress, the crushing stress, the shear stress and the circumferential stress. So these are the four stresses we will be looking into when we analyze the socket. Let us analyze the tensile stress induced in the slot of the socket. In this particular case, due to the forces, the failure will take place at this particular cross section, and the hashed area is the area under consideration. So we have to calculate the hashed area, but here we can see there is a slot which is there due to the cotter, which cannot be included, and in rather it has to be subtracted. Here we have made the diagram for that particular slotted area. Now the hashed area can be calculated in a way that the outer area minus the inner area subtracted by the slotted area. In this manner, we can formulate the equation. Now let us see. The outer area is pi by 4 d2 square minus pi by 4 d1 square. So we have taken the whole complete area, hatched area I mean, and then we have to subtract the slotted part. So the slotted part is d2 minus d1 multiplied by the thickness of the slot. So in this way the formula is formed. In this slide, we can observe the cross section of the area, and this is the 2D view given here in the slide. Now, let us calculate the values. We will substitute the value of P, and we know the value of D1. We know the value of design sigma T, that is the permissible sigma T. After substituting the values, we will get the value of D2. So D2 comes around 38.68, which can be approximated as 39 mm. In this particular slide, we will observe the crushing stress induced in the socket collar due to the cotter pin. Here we can see the 3D view, and here the socket is crushed because of the cotter pin. And you can see the blue color line is the area where the particular socket collar is being crushed. It is shown in the red color here. So we can find out the area here, that is D3 minus D1. Here there is a slot in between, therefore we have to subtract it. So we get it d3 minus d1 multiplied by t. So this is the projected area. Hence we have found the area in this particular case. Now let us substitute the values in the equation. In this particular equation, we know the known values, that is P, we know what is D1, we know what is T, and the design crushing stress we know. After substituting the known values, the unknown value, that is D3, can be found out, that is 59.37, which can be approximated to 60 mm. So hence we have found out the D3 parameter in this particular case. Let us look into the shear stress induced in the socket collar due to cotter pin. Here in this particular case, due to the load, the socket and the cotter pin gets pulled off, and this particular area from the socket collar gets sheared off. This particular area which we can see here is the hatched area, which is also shown here in the 2D form, and which is also shown here below. In this particular area, the break section here is the shade area. Now this area can be calculated as D3 minus D1. We are subtracting it because there is a slot in between. So D3 minus D1 multiplied by C will give us the area. So we can put on this equation P upon area. So area would be 2 into D3 minus D1 into C. Here in this equation, 2 is multiplied because there are two areas, area in the front and area at the back side. So this is a clear case of double shear, that's why we have multiplied by 2. So this ratio should be less than the permissible shear stress. Let us substitute the values in the equation. We know what is P, we know what is D3 and D1, we know permissible shear stress. After putting up this value, that is known values, we can find out the unknown value, that is C. So C comes out around 12.72, which is 13 mm. The circumferential shear stress induced in the rod end of the socket. In this 3D view, we can see that because of the pull, the rod end gets detached from the socket. And here, the red color portion, what you see is called as the resisting area, where D is the diameter and L1 is the length. Hence, the area becomes, because it's a circumferential area, the area becomes pi into D into L1. In this manner, we can formulate the equation. Let us substitute the values in this particular equation. In this equation, we know the known values, that is P, and we know what is the value of small d. Hence, from this equation, then after putting up the known values, the unknown value L1 it can be found out. The L1 comes around 10.56, which is approximately 11 mm. The direct shear stress induced in the cotter pin due to socket and spigot can be seen in this particular figure. In this figure, you can see because of the opposite forces, the cotter pin is sheared off in this particular location and in this particular equation. So there are two locations where this particular cotter is sheared off, and we can find out the area looking at the cross section, where B is the width of the cotter pin and T is the thickness of the cotter pin. So we have it as P upon area, where area is B into T multiplied by 2. So this is the clearly a case of double shear, that's why the 2 is here. And after putting up the known values, we can find out the small b. Small b comes out to be 38.18 mm, which can be approximated as 39 mm. So in this way, we have found out the width of the cotter. Now width of the cotter can be found out by using the shear stress, as well as it can be found out by bending stress. Let us look into the bending stress calculation. Bending happens due to opposite forces acting on cotter pin with respect to socket and spigot. Bending also happens due to clearance present in between cotter pin and with respect to spigot and socket. The bending analysis of the cotter pin is considered as simply supported beam. So in this figure, we can see that the cotter is shown in yellow color and the bending happens here. Now one can observe, because of the spigot, a uniformly distributed load is acting in this particular part, and because of the socket, a uniformly varying load is acting on this particular section of the cotter pin. So the cotter is subjected to uniformly distributed load in one side, that is here in the left side, and a uniformly varying load on the other side. This can be displayed here also. So we can clearly see the UDL and UAL acting on the cotter. Now we need to find out the bending stress, and the formula is the maximum moment multiplied by the Y max upon IYY. this should be less than the sigma t, design sigma t. So if we put up the values in this particular equation, we can find out the width of the cotter at the end. Now, when we try to find out the bending stress induced in the cotter, there are three rules when we will focus. When considering forces in bending stress in symmetric body, only half of the section of the body is considered. That is, forces acting on the half of the section will be considered. So when we look into the cotter, we will be only considering the top part, and the bottom part, because it is symmetric, we will leave it out. The distance between the forces and the center line is considered. So the forces intend to revolve towards the center of the body of the cotter pin. So this is the third thing we will consider. Now let us look into the cotter pin. We know that the above part is subjected to uniformly distributed load. So we will be taking a point load at the top section and also at the bottom section. So the P will be divided into P by 2 above and P by 2 below. And the total distance is also divided D1 by 2 and above and D1 by 2 below. So this is how we have distributed it on the left hand side. On the right hand side, because of the socket, you can see P by 2 force is acting at this particular point and P by 2 force is acting at this particular lower point. So these are the forces that are acting, and you have a varying load here and the varying load here. There is a slot in between here because of the spigot, and that particular load will not be considered here, but it is considered on the left hand side. With respect to the spigot, we will take it on the left hand side, and with respect to the socket, we will be taking on the right hand side. Here in this particular slide, we will be looking into the force P by 2, which is acting on the right hand side, and the distance from the center to the extremmost fiber here is d1 by 2, and the distance between the center and to the point of which the load is acting is z. So we are interested to find out what is z. In this particular figure, we can find out z is half the distance of d1 by 2. Therefore, the z becomes d1 by 4. Here, you can see the p by 2 is acting at distance of y. Now, the y is d1 by 2 plus the distance x. And here we don't know what is x, and that is the challenge. So if you know what is x, we can find out what is y, because the distance y is important to calculate moment. So let us go next and find out y and x. So in this particular slide, to find out x, it depends upon u. We can find out u. Now u is the distance between the bottom line and the top line. And we can see here the distance between the center line and the bottom line is d1 by 2. We can also observe the distance between the center line and the top line is d4 by 2. So using these two particular parameters, we can find out u. So in this slide, we can see that u is d4 by 2 minus d1 by 2. So in this manner, we can find out what is u. So once u is found out, we can say that u is equal to x plus v. So this is x distance and this is v distance. We are not very much concerned with what is v, but we are very much concerned to find out what is x. So from the concept of uniformly varying load, we know that x is 1/3 of u and v is 2/3 of u. Now we already found out what is u. We can substitute the u value into this particular equation of x and find out what is x. So this is what we have done. We have substituted the u value in this particular value of x, and we have found out what is the x. So x is 1/3 of, in bracket, d4 by 2 minus d1 by 2. Now the next challenge is to find out y. To find out y, we know that y depends upon d1 by 2 plus x. So x plus d1 by 2. So we can substitute the value of x here. So now our y becomes d4 minus d1 upon 3 by 2 plus d1 by 2. So in this way, we have found out y. And now we are in a position to substitute this x and y values in the moment equation. Here is a moment. Now you can see here the load P by 2 is acting at the distance of Z. The load V by 2 is acting at the distance of Y in the right hand side. To find out maximum moment, it is P by 2 multiplied by Y minus P by 2 multiplied by Z. We know what is Y, we have substituted the value of Y, and now we can substitute the value of Z. So this is how we finally get the maximum moment. Now, this is the moment what we have got. This moment can be simplified. So, taking LCM and finally simplifying it, we get maximum moment is equal to P by 2 in bracket D4 by 6 plus D1 by 12. So, in this manner, we have found out maximum moment in terms of diameter. The diameter D4 and D1 are known, so that is the advantage we have here. In the bending stress equation, we need to know what is maximum moment, which we have just found out. We will find out the moment of inertia. So moment of inertia is T into B cube by 12. Looking at this particular section, we can figure it out. And Y is the distance between the neutral axis and the farthermost fiber. So that is B by 2 distance. So all the three parameters we know, this can be placed in the bending stress equation. We have already seen the bending stress equation earlier, and after putting up this particular known values and substituting the values into the equation, we can find out B, that is the width of the cotter, and the B after calculation comes around 31.2, which can be approximated as 32 mm. Now, one can observe that we have found out B from direct shear stress as well as we have found out B from the bending stress. So, any one which is greater of the two we will consider. So, it is observed that the parameter 1 is quite greater in value. So, therefore, we will be taking the higher value here, which is B is equal to 39 mm. Few more parameters can be taken in consideration, that is to calculate the length of the cotter. So the length of the cotter pin can be taken as D4 plus some margin. So we can assume the margin as 10 mm and we know the value of D4. So length comes around 65 mm. Now we can calculate the slope of the cotter. Generally the slope is given only on one side and we will be considering the slope of the cotter. So we have taken the ratio 1 is to 30 here, and then it is equal to tan alpha is equal to B1 minus B2 upon L. Here one can observe tan alpha is opposite side upon adjacent side, where the opposite side is B1 minus B2 and the adjacent side is L. So that's what we have written here, tan alpha B1 minus B2 upon L. Now we can substitute the value. We have taken the ratio 1 upon 30 and we have already calculated the value of L. So value of L is 65 mm. So we can get here equation 1. Similarly, we know the average width. The average width is small b is equal to b1 plus b2 upon 2, where we have earlier calculated the average width to be 39 mm. After substituting here, we can get the equation 2. Now we have equation 1 and equation 2. We can solve them simultaneously and get the value of B1 and B2. So here B1 comes around 40.08 mm and B2 comes around 37.917 mm. We can also assume the clearance between the spigot and the cotter pin. We can assume it to be around 1.5 mm. At this point we will end the design.